All right, so let's talk about molecular geometry. 12.9, I can explain how molecules can have three-dimensional shape and an angle between bonds. That's called the Vesper model. And number 10, if given a molecule, I can determine the molecular structure, hybridization, whether or not it resonates, whether it is a dipole, bond angle, and for that molecule. Okay, yeah, right now that's going, no, but just give me a few minutes. Found out something amazing about Hank Green. I'm not sure whether now I respect him more or less. Apparently, there are a subgroup of heterosexual males which have a special gene that makes them like My Little Pony. And what I found out is that Hank Green is a brony. So some people think that now he's cooler. Others are going, what? Yes, these guys watch My Little Pony and are very serious about it. They love the plot lines, and they even have little My Little Pony action figures. What? I know, here we go.
Let's start with water, because all the interesting things on our planet start with water. It's also universally common, not just on our planet, but in our galaxy and our universe. Case in point, in 2011, astronomers discovered a cloud of water ice surrounding a black hole that contains 140 trillion times more water than we have here on Earth. And while we don't have any confirmed worlds covered in water outside of our solar system, we do have some right here in our solar system. Europa contains so much water, probably salt water, that its entire surface is just ice. What did any of that have to do with atomic orbitals? Nothing. I just felt like maybe I scared you with all that quantum mechanics talk before the intro, and I wanted to chill you out for a second. Okay, so water. We did its Lewis structure last week, remember? Each hydrogen bonding to the oxygen atom, and voila. But that drawing is linear, just a straight line through all the nuclei, and we know, just instinctually at this point, that water is a bent molecule. But why? Why is water crooked? Unbonded atoms within a molecule generally like to be as far away from each other as possible, especially if they have the same partial charge as the two hydrogens do with their partial positives. But something is keeping those hydrogens closer together than they would like to be. So why on earth are they not stretched out as far away from each other as possible? I ask this because if they were, the water molecule wouldn't be polar, and if water was suddenly nonpolar, we would all instantly die, as would all life on Earth. And suddenly we realized that this seemingly normal thing that we all knew about the world is really weird. And weird stuff is my favorite stuff because it means interesting questions. Interesting questions I want to know the answer to.
All right, so to draw these two, some of you have already probably finished the worksheet that I'm expecting you to finish, which is 12.3, right? Okay, you have finished that worksheet, and let me tell you that by and large, most of them are, even if they're completely right, by and large, most of them are wrong. Why? Because we live in a two-dimensional world. Okay, so tomorrow is due 12.2. I'm sorry, 12.2 is due tomorrow. Monday. 12.2 is due on Monday. 12.2 is probably mostly wrong. Why? Because we live in a three-dimensional world, and you guys drew two-dimensional objects. Yes.
We're still getting credit for these drawings.
Yes.
Right? Okay. Now okay.
Believe it or not, those two-dimensional objects that you drew for 12.2 really cannot help us explain the physical and chemical properties that even water has. Okay, water is dependent on the fact that it is a three-dimensional molecule. So the last part of this chapter that I need to teach you is how to determine the three-dimensionality of these molecules. Okay?
We spend a lot of time thinking about atoms as looking like this. There's a ball, and there's a stick, and there's another ball, and another stick. It's just a bunch of balls stuck together by these little wooden bonds. Simple, pretty easy to understand, and thus, as you have probably come to expect, it is entirely incorrect. Nuclei really can be understood as little balls, and that's more or less correct. Though when you get to some of the bigger, less stable ones, they start looking more oblong and weird, like a rugby ball. Atoms are basically ball-like as well, with electrons in a spherical cloud around the nucleus. But molecules, as we discussed last time, do not look like balls on sticks. Bonds don't form into neat little lines. They form from overlapping electron clouds, or shells, flowing around the nuclei of bonded atoms. If you really get down there and understand what they look like, they're like lumpy, clumpy globs of probable electron locations. And these lumpy clumps of probable electron locations do not behave the way you might initially expect them to behave. Oh no, that would be far too simple. They behave based on quantum mechanical, three-dimensional wave functions, probabilistic distributions of electrons in space. And yeah, by the end of this episode, you're gonna understand what I just said, and it's gonna be awesome.
So basically what he said is, yeah, their three-dimensionality is important.
These orbital configurations determine the shape of molecules, and the shape of molecules determines how they behave, what forms they take, what properties they have. It's pretty dang amazing, really, that wave functions determining the probable locations of electrons keep water bent and thus polar, and thus able to dissolve nutrients and form a stable home for our cells so that we can walk around as weird bags of mostly water, thinking about stuff, making YouTube videos, trying to learn more about the world, or maybe just trying to pass a test.
The rule, let's call it a model, that governs this is called the Vesper model. Valence shell electron pair repulsion model. The valence shell electron pair repulsion model. Marie,
Yeah.
living with my wife now for 25 years, I've learned a little bit about women. There's still a mystery to me.
Even to women are mystery.
Even to women, they're a mystery. You guys are just mysterious. You're amazing. Okay? For example, guys don't like each other. Usually, eventually, it leads to a fight. We fight. We get over it. Now we're best friends. You guys fight and you hate each other for the rest of your lives.
You shouldn't have worn those shoes.
Okay, my wife hates that girl in 3rd grade that she got into a fight. I mean, they're now both probably 48 years old. They're grandparents. It doesn't matter. If she was to find her on the street, she'd probably get into another fight with her. And they won't even know why they're fighting. Marie, are there some young ladies in your life that you absolutely hate?
Yes.
Okay? So, this is Marie right here. This stick represents the 2 electrons that are shared between this atom, and this is Marie. And this is the girl, let's call her Betty. This is the girl that she does not like. So, Marie, come over. Marie, get over. Get to where Betty. Marie, get to where Betty. Here comes Betty. Come on, Marie. Please, Marie. Just say I'm sorry and get it over with. Okay, it appears that this isn't going to happen. This is a valence shell. Is another name for outer shell electron. So this is an outer shell electron pair, and it is repulsed by the other outer shell electron pair. They don't like each other, and there's no way that I can get Marie to come over and kiss, love on Betty. Notice, I can't. I try and I try. I can be at this for days, and I can't get. Because of the Vesper model, electron pairs will repulse each other, and that's what gives these things its shape. Now, I want you to turn to this worksheet to the front. What I'm calling the front has tetrahedral. Tetrahedral is a geometric shape, and notice there's 3 of them. Why? Because there's 3 members of the tetrahedral family. Okay? It's ironic that Mr. Spock died today. Yes, let's have a 5-second pause of silence.
5 minutes.
Okay, we're done. Because this is usually the lecture in which I explain this whole concept of the USS Enterprise being a Constitution class ship. Okay, when engineers create a new type of ship, they make a prototype and they launch that prototype. The prototype that looked like the USS Enterprise was called the USS Constitution. So they launched it, and with a bunch of engineers on board, and the job of the engineer was to troubleshoot it. In other words, find the glitches. Something as complex as a ship or an app is going to have glitches. You guys are familiar with this because you know that when an app, you never go for the first time an app goes out because there's always lots of glitches. Okay, then they start making different versions of it. This is version 1.2, 1.3, 2.1, whatever. Okay, no one runs out and buys the brand new Windows because you want to wait about 6 months for them to fix it. Okay, you don't want to buy it when it's glitchy. Okay, in the same way, the USS Constitution is a glitchy ship. So when they come back to the space dock, they explain to all the engineers who helped to build it, this is what's wrong, this is what's wrong, this is what's wrong. So then they start building a new ship that fixes the glitches. The USS Enterprise was that second ship. What is it called? It's called a Constitution class ship. Why? Because it's based on the USS Constitution.
So it's a tetrahedral class.
Okay, so the tetrahedral class, there are 3 tetrahedral class ships. The first tetrahedral class, the first type of ship is going to be named after, well, the whole class is named after it. It is tetrahedral. So, on your worksheet, under shape, the first shape of the tetrahedral class is the flagship. It is the one that it was all based on, and that is called tetrahedral. So the first shape we're going to look at is called tetrahedral. No, you don't draw it. You just put down the word tetrahedral. The shape goes, yes, because it is called tetrahedral. Kind of like Jameson. Like, what's with that? You know, James.
You put that in all 3 of those boxes?
Jerome P. Jerome wrote 3 minutes.
No, just like the first one was Constitution class ship, USS Constitution, the second one has a different name. Okay? The first one is going to have 1, 2, 3, 4 shared pairs. 4 pairs of electrons surrounding the central atom, and all of them are shared. 4 shared pairs. How many of these pairs of electrons are unshared? None of them. They're all shared. 4 shared pairs, none unshared pairs.
Wait, what?
What?
Is this for the first thing?
We're not there yet. Okay. 4 shared pairs, 0 unshared pairs. Hybridization, do you remember what kind? That gave you 4 bonds?
Excuse me, please, for the announcement. Don't forget to catch the back.
All right, so the first shape we're going to look at is called tetrahedral. Tetrahedral. It has 4 shared pairs. 4 shared pairs. This guy has the same name as his last name. He is Mr. Tetrahedral, because he is the basic shape. Just like the USS Constitution is a Constitution class ship, tetrahedral is a tetrahedral family type shape. So his first name in chemistry, we use the last name first, tetrahedral, the first name last, tetrahedral. So tetrahedral. In 3 dimensions, and I don't understand this. This might be for a geometry teacher to talk about. You have an angle of 109.5 degrees. 109.5 degrees. 109.5 degrees. Okay? Now, it's hybridization. What is this hybridization stuff all about? Let me explain that to you. In order to have certain number of bonding sites, okay, a molecule, a central atom is going to have to be able to move electrons around in order to maximize its bonding sites. In the case of tetrahedral, you have something like CH4. Let's draw it. Carbon has 4, and hydrogen is 1 times 4, for a total of 8. Carbon's in the middle. 2, 4, 6, 8. Carbon normally has 2 in the S and 1 in the P, each P. But in order to be able to bond 4 times, it has to move an electron from the S into the final P orbital. We call this sp3. 1 electron in the S and 3 electrons in each of the 3 p orbitals. Okay? That's sp3. There are others. So if you need to be able to bond 4 times, it's sp3. If you need to bond 3 times, it's spp, sp2. If you need to bond 2 times, it's sp. If you need to bond 5 times, careful. You only have 1 s. Okay, so you use that up. You only have 3 p orbitals. You've used them up. That's 4. What's the next higher orbital? D. And if you need to bond 6 times, all right, so how do we draw this 2D? 3D, I'm sorry. I draw it like this. This is 2D. Now I'm going to draw it. You don't have to draw it this way, but I want to show you why it's called a tetrahedral. Imagine carbon's in the middle, and let's put some skin to this. And what do you have? A tetrahedron. 4 sides. 4 sides. A tetrahedron. Now, question. Is this a polar molecule or a non-polar molecule? Is it a dipole? Is it a polar molecule? Is there one side of this molecule where there's more electrons than the other? Let's go to our electronegativity chart. Carbon is 2.6, hydrogen is 2.2. So that means all of the hydrogen's electrons are leaning toward carbon. Leaning toward carbon. Okay? Which side? North, south, east, west. Which side is carbon in? Which side? North, south, east, west. Answer the question. Which side? Actually, probably not all, none. It's in the middle. It's going toward the middle, isn't it? Carbon's in the middle. Carbon's in the middle. And all the electrons are leaning toward the middle. This molecule is said to be symmetrical. It's the same on all 4 sides. So because of the symmetry, the forces cancel each other out. There is no side. inside and outside are not possible. If you're the answer to the question, who is the most electronegative side, is inside or outside, it's nonpolar. It's nonpolar. Okay? How about this one? Carbon bonded to chlorine, which is more electronegative. Chlorine is 3.1, I think. Carbon is 2.6. So let's draw the arrow toward chlorine now. Which side? North, south, east, west? None. The outside. Outside, right? Because all of carbon's electrons are leaning toward the outside. Those of you who saw it as leaning down, keep in mind that this is just a molecule that's just floating around. So if you don't like, what if I was to take this molecule and turn it upside down? Would it be up? Left? Right? See what I'm talking about? So there isn't a side here. Now, so this is nonpolar. Now, let me give you one that's polar so you can see the difference. Cl on top and H's down on the bottom. So the H's are leaning toward carbon and carbon's is leaning toward chlorine. North. This is the negative side. This is the positive side. Now, if you understand that, that's great. If you don't, here's the ultimate question. There's two questions. A, how many sides does this thing have? 4. Is it exactly the same on all 4 sides? This one, is it exactly the same on all 4 sides? Polar. This one, is it exactly the same on all 4 sides? Non-polar. This one, is it exactly the same on all 4 sides? Non-polar. So if the answer is yes, non-polar. The answer is no, polar. This guy's brother. His name is Pyramidal. We're going to take away a shared pair and add an unshared pair. This little ghost-like figure. This is an unshared pair. Okay? Why? Let me get rid. The angles are wrong. The angle between these, and the angles are only between shared pairs. The angle between the shared pair is 107 degrees. Why are these guys closer? Even though, do you not see, it's still a pyramid, right? It's kind of like a squashed pyramid or a tetrahedron, but it's still a pyramid. It is still a tetrahedral. It belongs to the tetrahedral family. But it's your brother, Pyramidal. Pyramidal. It's Pyramidal. Now, the question is, why are these guys closer together than they were back when it was 4 shared pairs? Because, well, what if I had a rubber band between me? I got one end of the rubber band and I gave it to Mark, the other end. Okay, Mark, hold it. All right. So we're stretching, coming back together, stretching, coming back together. Basically, a shared pair, 2 atoms sharing a pair of electrons are going to stretch the electron cloud so they don't take up as much space. Okay? So that's why it looks like this is right here, they're stretched. But an unshared pair is not stretched, so it just kind of goes, it's just kind of like a blob. That blob causes these guys to be pushed closer together. So that's why these guys' angle is 2.5 degrees smaller. Every one of these unshared pairs pushes the shared pairs by 2.5 degrees. By 2.5 degrees. All right, so tetrahedral. Tetrahedral, tetrahedral, tetrahedral pyramidal. Poster child, NH3. Nitrogen is 5, hydrogen is 1 times 3, 8. 2, 4, 6, 8. There's your 2D drawing. Shared pairs?
3.
Unshared pairs? Angle between these guys? 107. Why? Let me show you three-dimensionally. Blob with 2 eyes. It's still a tetrahedron. Let me show it to you. First of all, when we're determining shape name, it's based only on the shared pairs. It's kind of a squashed tetrahedron, but it's still a tetrahedron. Just kind of like pyramids are not true pyramids, not true tetrahedrons, are they? They're more like squashed tetrahedrons. They're not equilateral. The pyramids in Egypt are not equilateral, and they even have a square base. This has a triangular base. Okay, that's why it's called pyramidal. Hybridization, whether it's shared or unshared, does not matter. How many bonding sites? 1, 2, 3, 4. 1, 2, 3, 4. SPPP, SP3. All tetrahedrals have SP3. All tetrahedrals. So you might as well put SP3 down for bent as well. For the next one. Polar or nonpolar? Polar or nonpolar? Polar. Why? How many sides does it have?
It has 4 sides, but one of them is different.
Right. It has 4 sides, but one of them is different. Any questions on the first 2 family members of the family tetrahedral? So, tetrahedral, 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 pyramidal. You can almost imagine what I'm going to do next. Take away a bond and add another unshared pair. And what do we have? It's still a tetrahedron. Here's one side, here's another side, back here's another side, and down on the bottom is your 4th side. It's still a tetrahedron. We have 2 blobs. A blob is 2.5 degrees. It was 109.5. 2.5, 2.5 is 104.5. Hybridization. How many sides do you have? 4. Still 4 sides, so it's S, P, P, P. SP3. Okay, what is its name? Well, let me show you. What do you think it is? It looks like you've taken a linear molecule and you've done what to it? You've bent it. You've bent it. No, just called bent. Bent. I'll show you. Poster child, H2O. H is 1 times 2. Oxygen is 6. 8. 2, 4, 6, 8. Looking at water like that, you would say that it is nonpolar, right? That's 2D drawn. But that would be wrong. This is wrong. This is wrong. This is wrong. This is wrong. We got to draw it 3D. So, ghost H, ghost, H. Is it still a tetrahedron? Yeah, look at this.
It's like a flower.
It does not look like a flower.
I like flowers. Why is that bad?
It does not look like a flower.
It kind of does sound bad. What kind of flowers are you guys seeing?
Do you see that it's still a tetrahedron? Do you see that? Okay, but if you take away the unshared pairs, then that's all that it looks like. It looks like it's been bent. Now, be careful because this is called tetrahedral bent. There's a trigonal planar bent. The reason why we always use the last name is to distinguish because the shape name is going to be shared by several of these. And I am not going to give you every family member. Okay, Eddie will cover that in much more detail. I'm only going to give you the basics. Is this polar or non-polar? How many sides? 4 sides? Are they exactly the same?
Hydrogen, we've just got the 1s orbital. It's a sphere, marvelously uncomplicated. But in the second shell, we have an s orbital and 3 p orbitals. The p orbitals, if they were all by themselves, look like this. But when you actually stick them around an atom, the s and p orbitals start to interact with each other, doing their best not to overlap and changing each other. The s and the p orbitals can merge into hybrid sp orbitals. Instead of being 2 different kinds of orbitals, they become 4 identical orbitals trying their best not to overlap. This is called orbital hybridization. When the s orbital hybridizes with all 3 p orbitals, it's called sp3 hybridization, and it forms a tetrahedral shape. And this is that tetrahedral shape. It's the easiest way for all the orbitals to form something like a sphere around the atom, but not interact too much. I didn't do anything fancy to make these balloons take this shape. I just tied them together at the base. They naturally form this shape because they can't overlap with each other. And yes, this is exactly what's going on with water. In water, oxygen's 8 electrons are arranged with 2 in each sp3 hybridized orbital. 2 of those electrons are from hydrogen, 6 are from oxygen, including 2 lone pairs. Those lone pairs, even though they're not participating in any bonds, still have their orbitals. And so water is locked into that tetrahedral structure. No matter which orbital you stick the hydrogen atoms to, you're stuck with an asymmetrical molecule. That, along with the difference in electronegativities of oxygen and hydrogen, leads to the polarity of water and the existence of life.
All right, now let us travel to the new family. The new family, that's tetrahedral bent. Got it? Yes? Good? Okay. It's called trigonal planar. Let's add, wait. What do we have? What is this? What does it look like? Triangle. Trigonal in one plane. Here is an example of a molecule that does not need to exist in 3 dimensions in order to have the maximum angle. What is this angle? $120. Come on, this is something that you geometry students could have easily figured out. What is the hybridization? How many bonding sites? sp2. sp2. All right, our poster child is going to be somebody that we talked about last time. BCl3. Boron is 3. Chlorine is 3 times 7. That's 21. B, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Done. But wait. Boron is not happy. Unfortunately, there ain't a dang thing we can do about it. Because boron does not have that much flexibility. sp2 is about all it can do. Chlorine does not have any flexibility at all. It's completely full with one electron. So that's all it can do. It can only bond 3 times. Yes?
So it won't be like triple bond?
Can't. There's no way. Carbon gives you that flexibility by allowing you to move 1 over. Boron can't. Now, if boron was maybe, no, it can't. Okay, so what does that mean? That means we're stuck with 3 sides. Trigonal, planar. How many sides does this thing have?
3.
Is it exactly the same on all 3 sides? So it is nonpolar. Now I know that on this worksheet it doesn't really matter, but if you look on the back of 12.3, it asks you dipole, question mark. I'm asking you whether it's polar. So it's either yes or no. Dipole means, is it polar?
So it has
3 shared pairs, no unshared pairs.
Wow.
Is there a sibling to this? Of course.
Is its name just triangle?
This is trigonal planar, trigonal planar. This is the first child. Trigonal planar, trigonal planar. It does have a brother. What if there is a shared pair? 2 shared pairs and an unshared pair.
What's this one shape called?
This is called, well, you tell me. Let's take away, let's make this guy what is it? Bent. So this is trigonal planar bent. Not to be confused by tetrahedral bent.
Okay, so was the first one just like
Trigonal planar, trigonal planar. This is trigonal planar bent. Angle, what's the angle? No, because this squishy, mushy thing is actually going to push it further together than 120. 117.5. 117.5. What?
It always moves it over to.
This is still sp2. All trigonal planars have to be sp2. All right. Poster child here is SO2. 6, 2 times 6 is 18. Sulfur, 2, 4, 6, 8, 10, 12, 14, 16, 18. Is everyone happy?
No.
Oh.
Can you do a double bond?
Yes, you can. Sulfur has that flexibility. Boron does not. Because I'm a conservative, I'm going to go with the right. What does that mean?
You're right.
What does that mean?
You have to make everybody happy.
It has resonance. That means I have to draw another one. But what does this mean? It can be that one, or it resonates. Now, yes.
my friend only has to like put the R for the right resonance.
Okay. I told you this, that if it was up to me, R is really all you would need to do. Okay, but in the AP exam, they will expect you to be able to draw all resident structures, and I'm concerned about you getting used to the R.
Okay.
So on tests, I'll probably ask you just to put an R, but you need to be aware that on the AP, you hear like a high pitch. Help us. All right. Now, be careful here. I want to point something out. There are how many bonds? 4 bonds. But how many bonding sites? 3. And that's what makes it sp2. That's what makes it sp2.
So does it have 3 shared pairs?
It has a double and triple bond counts only as one thing. So we say that it has 2 shared pairs. A double bond counts only as one thing. Okay?
But sp orbitals can hybridize in other ways as well. How, for example, could you imagine sp3 orbitals forming a double bond? You can't have 2 orbitals mashing together in the same space, and sp3 orbitals are pretty much stuck in their tetrahedral structure. Well, if a molecule is going to be at its lowest energy state by forming a double bond, it has a nice simple solution. It only hybridizes 2 p orbitals with the s orbital, forming 3 sp2 hybridized orbitals with an unhybridized p orbital sticking up from the center. Tie balloons together like that, and you get what we call a trigonal plane. Each sp2 orbital is 120 degrees away from the other, drawing a line straight through their centers, and you get an equilateral triangle. One of the 2 bonds in the double bond has sp2 orbitals merging together nicely in line with the nuclei. This straightforward sort of bond is called a sigma bond. A second and weirder bond forms, this one from the unhybridized p orbital sticking out above and below the nucleus. These atoms merge to form a pi bond. That's your nice symmetrical double bond that you see in molecules like ethylene.
How much higher is that sound going to go? All right. Get rid of this, and that's all you have. What is the hybridization? How many bonding sites? 2, so it's S, P. Angle. Duh, 180.
This one's just called linear.
This is linear. And there are other linears, but we're only going to cover one. Linear, linear. Poster child. BeCl2. Be careful. Beryllium is a metal and really shouldn't do this, but it's so tiny that it can. Be has 2. 16. Pretty soon I won't be able to hear. The older you get, the harder it is to hear the higher pitch. So pretty soon I won't be able to hear it, and you guys will... No, you guys will have your heads exploding. All right, so BeCl2 is... What about the 3D? You can't make this 3D. It's just like trigonal planar. This is... It can only exist... It really only needs to exist in one dimension. It's a line. 2 dimensions. 2 dimensions. The line. Okay? Here's another one. Remember, double bonds are the same thing as a single bond. They exist in the same place. Here's another one. Remember, triple bonds, the same thing as one bond. Okay. Polar or nonpolar? How many sides? Exactly the same? Polar or nonpolar? Nonpolar? How many sides? Exactly the same? How about that one? Why? How many sides? 2 sides? Exactly the same? No. So Morgan is right. Polar. I can still hear it.
Can we not close this door?
Close the door, yeah.
Can I do it?
I don't know where that's coming from.
It's from in here.
Okay, how about this?
What on earth is it?
Okay, let's take it apart. You have the middle is a triangle, and then you have a top and a bottom. How many angles do you have? The middle has 120. The top is 90. Yes, two angles, 90 and 120. It is called a bipyramid. A bipyramid. A bipyramid. Let me see if I can explain to you. Oh, let's do linear first. Sorry.
And yes, sp orbitals, where the s only hybridizes with one p orbital, are also all over the place. These occur when an atom is either triple bonded to another atom or is double bonded to two atoms. The sp orbital, the one that forms the sigma bonds here, is linear. There are just two of them, balloons, easy, see, straight line. The trick is to have those two unhybridized p orbitals that can engage in two pi bonds, either to form a single triple bond or to form two double bonds, like in carbon dioxide. Carbon dioxide's orbital structure is actually really cool, so let's take a look at it as an example. The carbon is going to have two double bonds, so it has to have two unhybridized p orbitals and one sp hybridized orbital. The oxygens are going to have one double bond, so they need to set up as sp2 hybridized with one unhybridized p orbital for the double bonding. As they come together to bond, the sigma bonds will occur between the hybridized orbitals. Very simple. One oxygen will line up to form a pi bond with the vertically oriented p orbital from the carbon, and the other will line up with the horizontally oriented one. There you have it. Bond, 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 bond. And yes.
All right. Here we go. PCl5. PCl5. P is 5. Chlorine is 7 times 5. 40. 2. 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Yay, 40. That's 2D. 3D. One on top, one on the bottom. One behind you, one in front of you, and one to the side. Let's put some skin to it. Do you see the tetrahedron? Yes? Everyone look up here. Do you see the tetrahedron? Okay, there's another tetrahedron glued down to the bottom. So how many sides does this thing have? 2 tetrahedron with a tetrahedron base, 6 sides. 1, 2, back here's 3, in front 4, back here's 5, 6. 6 sides. 6 sides. Okay? 6 sides. A bipyramidal. Hybridization. How many sides? How many bonding sites? 1, 2, 3, 4, 5. S. P3 gives you 4. D.
But of course, as will always be the case in your unrelenting search for more knowledge, there is yet more to learn. DNF orbitals can hybridize with sp hybridized orbitals and with each other, forming some gorgeously peculiar geometries. And when 2d orbitals hybridize with sp3 orbitals, you get d2sp3, an octahedral structure, which those of you who play role-playing games will recognize as an 8-sided die.
All right. Octahedral. For those of you who've ever played Dungeons and Dragons, you'll be familiar with this. Probably most of you have not because it requires imagination. Look it up. That's probably a strange word for some of you. Using your imagination. All right, here we go. One on top, one on the bottom, and what is the base like? A square base. The other one was a triangular base. This is a square base. A square base. Angles? 90. And between the top and the bottom? 90. Everything's 90. 90, 90. 90, 90, 90. This is octahedral, octahedral. By the way, there are many members of the bipyramidal family. I'm only going to ask you to know one. There are many members of the octahedral. I'm only going to ask you to know one. Okay? When you get to AP, there'll be others. SF6 is like PCL5, an exception to the rule. So 2D, (3D), one on top, one on the bottom, two going back, two going forward toward you. So, you have a square base. So you have an Egyptian pyramid, yes? You know Egyptian pyramids are square-based, right? There are actually some nut jobs that believe that there's another Egyptian pyramid located below the Great Pyramid of Giza. Of course, when you start wondering, how did they do that? They also believe it was done by aliens. Okay, so this is, how many sides do we have? 1, 2, 3, 4 behind you. 1, 5, 6, 7, and 8 behind you. Octahedral, octahedral. What is the hybridization? Did we get everything?
Yeah.
Yep. All right. So I want you to turn the page around and practice.
No, no.
Nope.